The thermal expansion valve, the TX valve, is constructed of cadmium-plated steel or of aluminium. Three types are commonly used. These are internally equalized, externally equalized, and H-block. This section examines thermostats. When warm air passes across the evaporator fins, the cooling action causes water vapor in the air to condense and adhere to the fins in the form of water droplets. If the temperature of the fins drops to 0 degrees Celsius or below, ice will form on the fins, restrict the airflow, and prevent heat being transferred to the refrigerant. A thermostat is used to monitor the temperature of the evaporator fins and control system operation within set limits. The bellows type has a capillary tube that is placed about 25 millimeters into the evaporator core so that it contacts the fins. The capillary tube and bellows are sealed and filled with a temperature-sensitive fluid, which expands and contracts with temperature changes. This increases or decreases the pressure in the bellows. The bellows is positioned to open and close a set of contacts which form part of the electrical circuit to the compressor clutch. Springs connected between the bellows contact frame and the thermostat housing try to keep the contacts open. Pressure in the bellows tries to force the contacts closed. When the temperature at the evaporator fins falls below the minimum setting, the fluid in the capillary tube contracts, reducing the size of the bellows. The springs mounted on the pivoted frame move the frame to open the contacts and break the electrical supply to the compressor clutch. The compressor stops circulating refrigerant around the system and the temperature of the evaporator fins begins to rise. This increased temperature is applied to the fluid in the capillary tube, causing an increase in pressure at the bellows. The bellows pushes on the pivoted frame against the spring force and closes the contact points to complete the circuit to the compressor clutch once more. Circulation of refrigerant is resumed and system operation recommences. The thermostat usually cycles the system between a minimum of 2 degrees centigrade and a maximum of 8 degrees centigrade to maintain the evaporator at the required temperature. This section examines air conditioning system refrigerants. The refrigerant used for many years in automotive air conditioning systems is a substance known as dichlorodifluoromethane, commonly referred to as Freon, or R12. It is one of a group of gases called CFCs. R12 has the following properties. It is non-flammable, non-toxic, is stable at all temperatures, does not react with aluminium, steel or copper, and it is soluble in mineral oils. It also has a low boiling point and vaporizes at minus 30 degrees Celsius. However, it has recently been found to be harmful to the environment, and a number of alternative refrigerants have been considered to replace R12. The most practical of these being a liquid known as R134A. R134A is a refrigerant suitable for use in automotive air conditioning systems. It is an HFC, or hydrofluorocarbon. It does not contain the ozone-depleting chlorine atom. R134A has a boiling point of minus 26.2 degrees Celsius. All its other refrigerant characteristics are similar to R12. The only difference being that its operating pressures and temperatures in the evaporator and condenser are slightly higher than for R12. There are important differences in their chemical properties. Unlike R12, R134A is not soluble in mineral oils, so new compressor lubricating oils have been developed. To prevent the wrong lubricant or refrigerant being installed during servicing, the service ports on air conditioning systems have been changed so that the service equipment for an R12 system cannot be connected to an R134A system. This section examines pressure switches. High pressures and low pressures can cause severe damage to air conditioning system components. High-pressure switches are mounted in the high-pressure side of the system and have their switch contacts in series with the compressor clutch circuit. If the pressure exceeds the switch setting, the switch will open circuit the compressor clutch and the compressor will stop circulating refrigerant. Low-pressure switches are mounted in the low-pressure side of the system and are also connected in series with the compressor clutch. Low pressures can occur in air conditioning systems when the refrigerant has escaped. With no refrigerant flowing, lubricating oil flow is also reduced, and this can damage the compressor. Low pressure causes the contacts in the low pressure switch to open and break the electrical supply to the compressor clutch and stop its operation. This section examines the electronic control unit for automatic air conditioning systems. An automatic air conditioner is a manual air conditioner and heating system equipped with sensors which detect changes in ambient temperature, cabin temperature, and solar radiation. The electronic control unit evaluates the signals from the sensors to determine the operating conditions, and outputs actuators to move dampers and valves to control the throughput, temperature and direction of the air delivered by the system. The climate control system can be operated in manual mode, where the operation is similar to a normal heater and air conditioner system. The driver determines where the air is delivered, the volume of air delivered and its temperature. Or it can be operated in full automatic mode. In full automatic mode, the electronic control unit receives signals from sensors and controls the flaps and valves of the heating and air conditioning systems to create a blend of air that matches the temperature that is selected by the occupants. The electronic control unit, or ECU, contains a microcomputer. It is constructed from printed circuitry and has a large number of electrical components and electronic devices. It is normally housed in a metal or plastic container, and on some automatic climate control air conditioning systems, the control panel is part of the electronic control unit. The electronic control unit receives signals in the form of voltages from the ambient air temperature sensor, the cabin air temperature sensor, the coolant temperature sensor, the evaporator temperature sensor, sun load sensor, and the control panel. The electronic control unit compares these voltage values with values stored in its memory. If a difference in values occurs, the electronic control unit changes the position of actuators. The actuators are electric solenoids and electric motors which control the position of doors and taps either directly or by vacuum servos. The electronic control unit also controls the speed of the interior ventilation fan. The speed of the fan is infinitely variable between a stopped condition and the fan's maximum speed. Some actuators provide a feedback signal to the electronic control unit in the form of a voltage signal. This signal is used by the electronic control unit to determine what position the actuators are in and whether or not they are moving. When placed in automatic mode, the electronic control unit uses the last operator desired cabin setting. For this example, 24 degrees Celsius. The electronic control unit checks the temperature of the outside air, called the ambient air temperature. This is registered by the ambient air temperature sensor at 28 degrees Celsius. The car is parked in bright sunlight, so the radiation from the sun has heated the cabin air temperature to 45 degrees Celsius. The sun load sensor registers that the vehicle is in bright sunlight. When the engine has started and the climate control system is functioning, the electronic control unit switches on the air conditioning compressor and increases the speed of the interior ventilation fan. Air is drawn into the fan either from outside the vehicle or from within the cabin. The air then flows through the air conditioning evaporator core where heat is removed. The cold air-conditioned air is directed by flaps and ducts throughout the cabin of the vehicle, absorbing heat from the vehicle cabin and occupants, and thus lowering the temperature. The cabin air temperature is continually measured by the cabin air temperature sensor. When the cabin air temperature has been lowered to within approximately 2 degrees Celsius of the desired selection, the fan speed is gradually reduced. To achieve final control, the heater circuit may be opened and a blend door may be moved to direct some of the cold air-conditioned air through the heater core to provide fine temperature control. Both the fan speed and blend door openings are variable. If the vehicle is driven from sunlight into shade, less radiated heat is applied to the cabin interior through the cabin glass. The climate control system will have less heat to remove from the cabin of the vehicle. A sun load sensor located on the dash changes the signal that it sends to the electronic control unit. The electronic control unit registers this change in signal and will usually increase the amount of air that can flow across the heater core to compensate for the lower amount of heat radiated into the cabin. As the vehicle is driven out of the shadow, the sun load sensor again changes its output, and this is registered by the electronic control unit. More sunlight means more heat radiated to the cabin interior through the cabin glass, so the amount of air flowing through the heater core may be reduced. Many electronic control units have a self-diagnostic function, which assists in locating faults that may be present in the electric system of the climate control system. Fault codes can be displayed on the vehicle's display screen. Each code represents a circuit and components whose signals are outside of the limits expected by the electronic control unit. The fault codes are stored in the electronic control unit's memory until they are cleared during servicing. This section examines servo motors for automatic climate control air conditioning systems. Servo motors are used to control flaps and valves in the heater and air conditioning systems. By repositioning the flaps and valves, the output temperatures can be adjusted to the temperature desired by the occupants of the vehicle. Servos can be one of two types: vacuum servos and electrical servos. Vacuum servos consist of a sealed housing divided by a flexible diaphragm. The diaphragm seals the housing into two separate chambers. One of the chambers is open to the atmosphere. The other side is sealed and has a fitting for a vacuum hose connection. A spring forces the diaphragm towards one side when no vacuum is applied to the diaphragm. A linkage from the diaphragm connects it to the component to be moved. When vacuum is supplied to the sealed side of the diaphragm, a difference in air pressure occurs across the diaphragm. The force developed overcomes the spring force and the diaphragm moves, compressing the spring and moving the linkage. Admitting air to the vacuum side of the diaphragm allows the spring to return the diaphragm to the rest position. Some diaphragms use two sealed chambers, with neither end open directly to the atmosphere. When movement is desired, vacuum is applied to one side of the diaphragm and atmospheric air pressure to the other. The vacuum delivered to the diaphragm chamber can be controlled by a solenoid valve. When the electronic control unit wants to move a damper flap, it grounds the electrical circuit for the solenoid winding. Vacuum from a storage tank is applied through the solenoid valve to the diaphragm. To release the diaphragm, the electronic control unit open circuits the solenoid, and the diaphragm returns to the rest position. Movement of flaps and valves can also be achieved by using electrical motors that respond to output signals from the electronic control unit. An electrical servo motor is used to move the blend door. It incorporates limit switches to open circuit the motor when the maximum travel of the door has been reached. This stops the motor from burning out. Some electrical servos also utilize a carbon film potentiometer to signal to the electronic control unit the position of the blend door and, if it is moving, the direction in which it is traveling. A voltage from the electronic control unit is applied across the potentiometer. The wiper is connected by the signal wire to the electronic control unit. For maximum cooling effect, the blend door is moved to stop airflow through the heater core, and in this position, the voltage signal back to the control unit is at its lowest value. As the blend door is moved to allow airflow through the heater core, the voltage at the signal wire progressively increases until, at the maximum heat position, the voltage signal is at its highest. The control unit is thus aware of the blend door position, movement, and direction of travel. This section examines sensors for automatic climate control air conditioning systems. The electronic control unit needs to know the temperature of the outside air, the cabin air temperature, the temperature of the air conditioning evaporator, the temperature of the coolant circulating through the heater core, and if the vehicle is in bright sunlight. In most instances, the temperature sensors used in the climate control air conditioning system are thermistors. Although they may vary in appearance, their general operating characteristics are the same. These are solid-state electronic devices that change their resistance in response to temperature. As the temperature of the sensor increases, the resistance decreases. They are known as NTC resistors, as they have a negative temperature coefficient. When connected into a circuit, the sensor changes the voltage at the electronic control unit. The electronic control unit reads the sensor voltage as the temperature and compares this reading with information stored in its memory. The ambient air temperature sensor measures the temperature of the outside air. It is usually located in front of the air conditioning condenser, where the forward motion of the vehicle and the action of the condenser fans forces air over the sensor. If the outside air is cold, the resistance of the ambient air temperature sensor will be high, and the voltage at the electronic control unit will be high. If the outside air temperature sensor is hot, the ambient air temperature sensor resistance will be low, and the voltage at the electronic control unit will be low. The cabin air temperature sensor is mounted in a tube-type device called an aspirator. One end of the tube is open to cabin air, and the other is connected to the interior fan. Operation of the interior fan creates a flow of air through the aspirator. The temperature of the cabin air flowing through the aspirator controls the signal sent to the electronic control unit. The evaporator temperature sensor is located in the airstream, where the air leaves the evaporator and signals to the control unit the temperature of the air. The coolant temperature sensor for the engine management system signals to the climate control ECU the temperature of the coolant flowing in the heater core. Some climate control systems have a separate coolant temperature sensor, usually located near the engine management coolant sensor. The signal from the coolant temperature sensor is used in conjunction with the signals from the ambient air sensor, the sun load sensor, and the cabin air temperature sensor to control heater and fan operation. For example, if the electronic control unit registers the following readings: coolant temperature 16 degrees Celsius, ambient air temperature 0 degrees Celsius, sun load 0, cabin air temperature 0 degrees Celsius, the heater tap will open fully, the blend door will move to maximum airflow across the heater core, and the fan speed will be slow and steady. The sun load or solar sensor is located on the dash panel, where it is exposed to light entering through the windscreen of the vehicle. This sensor is a photodiode. It becomes more conductive as the light intensity increases. When connected to the electronic control unit, a change in light intensity is registered as a change in voltage. Other inputs to the electronic control unit come from the operator's control panel. The operator can tell the electronic control unit where to deliver air using switches which produce an on-off type signal. The unit will also receive instructions from the operator regarding the desired cabin temperature required. The desired temperature selection is used to tell the electronic control unit what temperature the operator wishes the inside of the vehicle to be. The electronic control unit then adjusts the position of valves and flaps to achieve the desired temperature. This section examines blower speed controls. The blower motor supplies the airflow to move air around the inside of the passenger compartment. It is located in the ventilation system before the air conditioning evaporator. In a manual air conditioner, the switch connects resistors in series with the motor to control its speed. The higher the resistance connected in series with the motor, the slower that motor will operate. Reducing the series resistance increases the motor operating speed. Most air conditioning systems use 2 resistors to give 3 driver selectable speeds of the fan motor. In climate control systems, the speed of the fan motor can be controlled electronically by the control unit modulating a pulse width signal. A longer pulse width will produce a higher fan speed. The electronic control unit changes the fan motor speed automatically depending on the difference between the interior cabin temperature and the set temperature. When the difference in temperature is large, the fan speed is increased to increase air circulation through the cabin. When the difference in temperature decreases, the fan motor speed decreases. This gives an infinitely variable fan speed between 0 and maximum speed. The change is progressive.